Hello and welcome. In this video, we'll be exploring binomial expansions for cases where the power is not a positive integer. By the end of this lesson, you will be able to expand expressions of the form a plus x to the power of n, where n is a negative integer or a fraction. You'll also learn how to combine this skill with partial fractions to expand more complex rational functions. Let's start by recalling the standard binomial expansion formula. The expansion of 1 plus x to the power of n is 1 plus n, x plus n times n minus 1, over 2 factorial times x squared, and so on. This formula is valid for any integer or fractional value of n as long as the absolute value of x is less than 1. But what if the first term in the bracket isn't 1? For example, what if we have a plus x to the power of n? In this situation, we must first factor out the a from the bracket. This gives us a times 1 plus x over a, all raised to the power of n. Using the laws of indices, this becomes a to the power of n, multiplied by the expansion of 1 plus x over a to the power of n. Now the expression inside the second bracket is in the familiar 1 plus y to the power of n form, where y is x over a. We can apply the binomial expansion formula directly to this part. So, the full expansion of a plus x to the power of n is a to the power of n times the series 1 plus n times x over a plus n times n minus 1 over 2 factorial times x over a squared, and so on. This expansion is valid when the absolute value of x over a is less than 1, which means the absolute value of x must be less than the absolute value of a. Let's work through a few examples to see this process in action. Our goal here is to express these expressions in the form a to the power of n times 1 plus x over a to the power of n. First, let's look at 5 minus x to the power of negative 3. The first term in the bracket is 5, so we factor out 5. This gives us 5 times 1 minus x over 5, all raised to the power of negative 3. Notice that we divide both terms inside the bracket by 5. Now we apply the power of negative 3 to both parts of the product. This becomes 5 to the power of negative 3 times 1 minus x over 5 to the power of negative 3. Remember, the power applies to the 5 as well. Finally, we simplify 5 to the power of negative 3. 5 to the power of negative 3 is 1 over 5 cubed, which is 1 over 125. So the expression is 1 over 125 times 1 minus x over 5 to the power of negative 3. We have successfully put it in the desired form. Let's try another one, this time with a square root. We want to express the square root of 2 minus 6x in the same form. First, it's helpful to rewrite the square root using a fractional exponent. The square root of an expression is the same as raising it to the power of 1/2. So we have 2 minus 6x to the power of 1/2. Now the first term in the bracket is 2. We factor it out. This gives us 2 times 1 minus 3x, all raised to the power of 1/2. Using square brackets can make the grouping clearer. Next, we apply the power of 1/2 to both factors. This becomes 2 to the power of 1/2 times 1 minus 3x to the power of 1/2. And 2 to the power of 1/2 is simply the square root of 2. So our final form is the square root of 2 times 1 minus 3x to the power of 1/2. For our final preparation example, let's look at a fraction. We need to express 32 over 4 plus 2x squared in the correct form. The first step is to get rid of the fraction by moving the denominator to the numerator with a negative exponent. This gives us 32 times 4 plus 2x to the power of negative 2. Now we focus on the bracketed term. The first term inside is 4, so we factor it out. This becomes 32 times the quantity, 4 times 1 plus 1/2 x, all raised to the power of negative 2. Next we apply the power of negative 2 to both factors inside the square brackets. This results in 32 times 4 to the power of negative 2 times 1 plus 1/2 x to the power of negative 2. Finally, we simplify the numerical part. 4 to the power of negative 2 is 1 over 4 squared, which is 1 over 16. So we have 32 times 1 over 16, which simplifies to 2. Our final expression is 2 times 1 plus 1/2 x to the power of negative 2. Now that we're comfortable with the preparation, let's tackle a full expansion problem. We need to expand 1 over the square root of 4 plus x in ascending powers of x up to the term in x squared and simplify the coefficients. As before, our first step is to rewrite the expression in the form a to the power of n times 1 plus x over a to the power of n. First, we write the square root as a power of 1/2, and then move the term to the numerator with a negative exponent. This gives us 4 plus x to the power of negative 1/2. Next, we factor out the 4 from the bracket. This becomes 4 times 1 plus x over 4 to the power of negative 1/2. Applying the power to both factors, we get 4 to the power of negative 1/2 times 1 plus x over 4 to the power of negative 1/2. We simplify the numerical part. 4 to the power of negative 1/2 is 1 over the square root of 4, which is 1 over 2. So our expression is 1/2 times 1 plus x over 4 to the power of negative 1/2. Now that we have the expression in the correct form, we can perform the binomial expansion. We need to expand 1 plus x over 4 to the power of negative 1/2. Here, n is negative 1/2, and r, x, term in the formula, is x over 4. Let's write out the first 3 terms of the expansion. The expansion is 1 plus n times x over 4 plus n times n minus 1 over 2 factorial times x over 4 squared. Substituting n equals negative 1/2, we get 1 plus negative 1/2 times x over 4 plus negative 1/2 times negative 3/2 all over 2 times x over 4 squared. Now let's simplify each term. The first term is 1. The second term is negative 1/2 times x over 4, which is negative x over 8. For the third term, the numerator is 3 over 4, and the denominator is 2, so the fraction is 3 over 8. This is multiplied by x squared over 16, giving us 3x squared over 128. This is the expansion of the bracketed term. Now we need to multiply the entire series by the 1/2 we factored out earlier. So 1 over the square root of 4 plus x is equal to 1/2 times our expansion. Distributing the 1/2, we get 1/2 minus 1/16 x plus 3 over 256x squared, and so on. Finally, we must state the condition for which this expansion is valid. The expansion is valid when the absolute value of r, x, term, which was x over 4, is less than 1. This simplifies to the absolute value of x being less than 4, or x being between negative 4 and 4. It's crucial to include this condition in your final answer. Now, let's move on to a more advanced application, combining binomial expansions with partial fractions. This technique is used to expand complex rational expressions that don't fit the simple a plus x to the power of n form. The strategy is to first decompose the complex fraction into simpler partial fractions. Each of these simpler fractions can then be expanded using the binomial theorem we just learned. Let's look at an example. We want to expand 1 over the quantity x plus 1 times x minus 1 squared. The first step is to express this fraction in partial fractions. This is a standard technique you may have seen before. The decomposition is 1 over 4 times x plus 1 minus 1 over 4 times x minus 1 plus 1 over 2 times x minus 1 squared. We will now expand each of these 3 terms separately. Let's expand the first term. We have 1 over 4 times x plus 1. We can rewrite this as 1/4 times 1 plus x to the power of negative 1. Now we expand 1 plus x to the power of negative 1. Using the formula with n equals negative 1, we get 1 minus x plus x squared, and so on. Multiplying by 1/4, we get 1/4 minus 1/4 x plus 1/4 x squared. This expansion is valid for the absolute value of x less than 1. Next, let's expand the second term. We have negative 1 over 4 times x minus 1. It's crucial to rewrite x minus 1 as negative 1 times 1 minus x. This allows us to get the apid, 1, at the beginning of the bracket. Now we expand 1 minus x to the power of negative 1. Using the formula with n equals negative 1 and our x term being negative x, we get 1 plus x squared, and so on. Multiplying by 1/4, we get 1/4 plus 1/4 x plus 1/4 x squared. This is also valid for the absolute value of x less than 1. Finally, let's expand the third term. We have 1 over 2 times x minus 1 squared. Again, we rewrite x minus 1 as negative 1 times 1 minus x. Squaring this gives us 1 times 1 minus x squared. So the expression becomes 1/2 times 1 minus x to the power of negative 2. Now we expand 1 minus x to the power of negative 2. Using the formula with n equals negative 2 and our x term being negative x, we get 1 plus 2x plus 3x squared, and so on. Multiplying by 1/2, we get 1/2 plus x plus 3/2 x squared. This is also valid for the absolute value of x less than 1. We have now expanded all three partial fractions. The final step is to combine them. We need to add the expansion of the first term, subtract the expansion of the second term, and add the expansion of the third term. Let's group the terms by powers of x. For the constant term, we have 1/4 minus 1/4 plus 1/2, which equals 1/2. For the x term, we have negative 1/4 x minus 1/4 x plus x. This simplifies to 1/2 x. For the x squared term, we have 1/4 x squared minus 1/4 x squared plus 3/2 x squared. This simplifies to 3/2 x squared. Putting it all together, we get our final expansion. The expansion of 1 over x plus 1 times x minus 1 squared is 1/2 plus 1/2 x plus 3/2 x squared, and so on. Since all three individual expansions were valid for the absolute value of x less than 1, the combined expansion is also valid for the absolute value of x less than 1. Let's look at one more example, this time involving a quadratic factor in the denominator. We want to expand 2x squared minus x plus 6 all over x plus 1 times x squared plus 2. First, we need the partial fraction decomposition. This is the case with a linear factor and an irreducible quadratic factor. The decomposition is 3 over x plus 1 minus x over x squared plus 2. We will expand these two terms separately. Let's start with the first term. We have 3 over x plus 1, which is 3 times 1 plus x, to the power of negative 1. Expanding this gives us 3 times 1 minus x plus x squared minus x cubed, which is 3 minus 3x plus 3x squared minus 3x cubed. This is valid for the absolute value of x less than 1. Now for the second term, which is a bit more involved, we have negative x over x squared plus 2. We can write this as negative x times x squared plus 2 to the power of negative 1. We need to factor out the 2 from the bracket to get it in the 1 plus y form. This becomes negative x times 2 to the power of negative 1 times 1 plus x squared over 2 to the power of negative 1. This simplifies to negative x over 2 times 1 plus x squared over 2 to the power of negative 1. Now we expand the bracket. Notice that our x term in the formula is x squared over 2. The expansion is 1 minus x squared over 2 plus x squared over 2 squared, and so on. This simplifies to 1 minus x squared over 2 plus x to the 4th over 4. Multiplying by negative x over 2, we get negative x over 2 plus x cubed over 4 minus x to the 5th over 8. This expansion is valid for the absolute value of x squared over 2 less than 1, which means the absolute value of x is less than the square root of 2. We have expanded both terms. Now we combine them by subtracting the second expansion from the first. We need to find the overlap of the two validity conditions. The first expansion was valid for the absolute value of x less than 1, and the second for the absolute value of x less than the square root of 2. The overlap is the smaller of the two intervals, which is the absolute value of x less than 1. Let's write out the combined expansion up to the x cubed term. We have 3 minus 3x plus 3x squared minus 3x cubed minus negative x over 2 plus x cubed over 4. Now we group the terms by powers of x. The constant term is 3. The x term is negative 3x minus negative x over 2, which is negative 3x plus x over 2, giving negative 5x over 2. The x squared term is just 3x squared. And the x cubed term is negative 3x cubed minus x cubed over 4, which is negative 13x cubed over 4. So the final expansion is 3 minus 5x over 2 plus 3x squared minus 13x cubed over 4, valid for the absolute value of x less than 1. Let's quickly recap what we've learned today. We started by extending the binomial theorem to cases where the power n is not a positive integer. The key was to factor the expression into the form a to the power of n times 1 plus x over a to the power of n, and then apply the standard expansion. We then saw how to combine this with partial fractions. This powerful technique allows us to expand complex rational functions by breaking them down into simpler parts that we can expand individually. Remember to always check the validity condition for your expansions, as they are only accurate within a specific range of x values. You are now equipped to handle a wider range of binomial expansion problems. Thank you for watching.